Welcome to the Deep Dive, where we cut through the noise and get straight to the insights. Today, we're plunging into something really crucial, kind of behind-the-scenes tech that powers so much modern AI, model quantization. Our mission really is to unpack how we make these machine learning models efficient, fast, scalable, moving beyond the basics to get into the advanced stuff, the surprising facts that actually drive AI deployment today.
Yeah, absolutely. If you've ever wondered how these huge AI models, billions of parameters sometimes, how they run on your phone or give you instant results from a server, this is pretty much the secret sauce. Because deploying these big models, it's tough, really tough. Size, speed, it's a challenge. This deep dive should give you a shortcut, like a real understanding of the nuances involved.
And we've got some great sources to guide us. There's a really comprehensive developer guide, Advanced Model Quantization, from PTQ to Frontier, and also a great Q&A deep dive that distills a lot of the key ideas. So for you listening, the big question we're tackling is, how do we actually shrink these massive AI models without, breaking them? And why is that so incredibly critical for everything from the cloud down to the phone in your pocket? Okay, so let's unpack this. Model quantization. What is it at its core? Well, basically, it's about changing the numbers inside the model, the parameters, right? Like weights, activations, the data flowing through. You take them from high precision, like 32-bit floating point, FP32 they call it, and you convert them to lower precision. Usually it's 8-bit integers, INT8. That's the most common target.
Exactly. And the payoff, it's immediate. It's compelling. You're looking at potentially a 4 times reduction in model size, which means way less memory bandwidth needed. And crucially, much faster calculations if your hardware has those specialized integer math units. And this isn't just nice to have, it's absolutely vital for getting models onto all sorts of hardware. Big cloud GPUs, sure, but also those tiny edge devices, phones, IoT sensors, that kind of thing.
Yeah, a 4x size cut and faster speed.
Yeah.
It sounds almost too good to be true, right? Like magic. But here's the catch, the unexpected twist.
Yeah.
That efficiency, it comes with a serious trade-off. If you're not careful, you can genuinely break the model. It's not just flipping a switch. It's this really delicate balance, isn't it? Between speed, accuracy, and deployment efficiency, memory, binary size, all that. Do it wrong, apply it naively, and boom, your accuracy could just plummet. Makes the whole optimization pointless.
You hit the nail on the head. The real art is minimizing that accuracy hit. And to really get into how we do that, we need to ground ourselves in the standard tools people use.
Yeah.
We're talking about PyTorch, mostly for its flexibility, allows for really fine-grained control, especially for advanced things like Quantization-Aware training or QAT. Then there's ONNX, that's the Open Neural Network Exchange. Think of it like a universal translator for models, or maybe a standard blueprint.
A blueprint, yeah, so you design it once.
Exactly. And ONNX lets it run anywhere, on any hardware, without the runtime needing to know how it was originally trained. It decouples the model, which is super important. And finally, ONNX runtime. That's the high-performance engine that actually runs the ONNX model. It's packed with optimizers. It has this flexible execution provider system for different hardware. And critically, it supports both main ways of doing quantization. Post-training quantization, PTQ, and running models train with QAT.
Okay, so we know what it is, why it matters. The big question for developers is often, okay, how do I get started? What's the fastest way? And that leads us straight into post-training quantization, PTQ. Apply it after training, no retraining needed. Sounds simple, but you mentioned challenges.
Oh yeah, simple on the surface. So remember, quantization maps floats to integers. You need 2 numbers for that mapping, a scale and a 0 point. Scale is like how big is each integer step in the original float world. 0 point is just where does the original float 0 land on the integer scale. Now, within PTQ, the big split is how you handle the activations that data flowing between layers. 2 main ways, dynamic versus static. Okay, first, post-training dynamic quantization, PTQ QAT. Here, the weights. You quantize them offline to INT8. Done. But the activations, they're handled dynamically, like on the fly during inference. For each activation tensor, the system looks at its min-max values right then, calculates the scale in 0 point, and then does the operation. Pros. It's simple, often just plug and play, no special dataset needed. And it's robust if your activation values jump around a lot. Cons. There's a little bit of overhead during inference, right? Calculating those parameters takes time. It's often good for models like transformers, BERT, or RNNs, LSTMs, where activations can be unpredictable.
Okay, dynamic handles activations on the fly. Then, post-training static quantization, PTQ, yes. Sounds like it does the work beforehand.
Exactly. PTQS quantizes both weights and activations offline. But to do the activations, you need this extra step, Calibration. You take a small data set, maybe 100, maybe 1,000 samples. It's representative of your real data. You run it through the model, and observers collect stats on the activation ranges. These stats are used to calculate fixed scale and zero-point values, which get baked right into the model. The huge pro. Fast as possible inference, no runtime overhead for quantization, the big con. It completely depends on that calibration data. If your calibration set isn't truly representative, your fixed parameters are wrong, and accuracy can tank.
Mr.
Hard.
Sean.
Yeah, so PTQ QAT is great for latency critical stuff, especially edge devices. And it works best when activations are pretty stable, like in many CNNs, convolutional neural networks.
Right. And this choice, dynamic versus static, it's not just academic. It's a core engineering decision, isn't it? It really impacts how your AI behaves in the wild. This is where, you listening have to think about your specific constraints.
Yeah.
PTQD pushes the complexity to runtime. You trade a tiny bit of latency for simplicity and robustness. PTQS pulls all that complexity offline into calibration. You put in the upfront work, finding good data, setting up the process, but you get the absolute lowest latency back. So it's not just use dynamic for RNN, static for CNNs. It's what are your needs? Cloud service, maybe handling diverse data. Throughput is key. A tiny latency hit is okay. Dynamic might be pragmatic, but real time on an edge device. Strict latency budget. That upfront work for static quantization might be the only way. It might be mandatory.
That's exactly the trade-off. And with PTQ everything hinges on that calibration quality. The goal is finding the best scale and zero point for each activation tensor. And the number one enemy here, outliers. Just one single crazy value way outside the normal range.
Like that freezer door example you mentioned earlier.
Kind of, yeah. That one outlier forces your quantization range to stretch way out to cover it. And when the range stretches, all the normal useful data points get squashed together. They lose resolution. Precision drops. Accuracy drops. So advanced calibration methods, they're all about dealing with those outliers smartly.
Okay, so let's get into that art. If the basic min-max calibration is just finding the absolute minimum and maximum, what are the smarter ways? On NX runtime, other tools, they offer different algorithms, right?
They do. So min-max is basic, fast, but yeah, super sensitive to outliers, often gives poor accuracy because of that. Then you have methods like entropy, sometimes called KL divergence-based. This is more theoretically grounded. It tries to find a clipping range that minimizes the information loss between the original FP32 distribution and the quantized INT8 one, often gives better accuracy.
Okay, what else? I heard about percentile.
Right, percentile is very practical, very robust. Instead of using the absolute min-max, it picks a percentile, say the 99.99th percentile, to set the clipping range. It basically just ignores the most extreme outliers. NVIDIA uses this, calls it percentile quant. It's often a really good balance between speed and accuracy.
Makes sense. Ignore the crazy values.
Pretty much. And then there's mean squared error, or MSE. This one directly tries to minimize the numerical difference, the error, between the original values and the values after you quantize and then dequantize them back.
So for you listening, picking the right calibration method isn't just a detail, it's a critical choice. A hyperparameter really impacts accuracy. It's about finding the real range, ignoring the noise.
Precisely. It's a data-driven decision.
Yeah.
Clean data, maybe min-max is fine. Data with long tails, outliers, you'll likely need percentile or entropy to get decent results. It's engineering, making an informed choice.
Okay, beyond calibration, you mentioned two other things that fine-tune this. Symmetry and granularity. They affect scale and 0.2.
Absolutely. These are kind of orthogonal choices, but also super important for accuracy and hardware performance. First, symmetric versus asymmetric quantization. Symmetric means your float range is centered on 0, like NH MM, and you map that to an integer range also centered on 0, maybe Megish 127 for signed INT8. Crucially, float point 0 maps perfectly to integer 0. The 0 point is always 0. This can simplify the math, make it faster on some hardware. Asymmetric, on the other hand, uses the actual observed min and max, maximum vol. This range isn't usually centered on 0, so you map it to the full integer range, and you often need a non-zero 0 point to represent 0.0 accurately. It's more flexible, generally gives higher accuracy for skewed data not centered around 0, because it uses the integer range better.
Okay, symmetric versus asymmetric, and the other one was granularity, per tensor versus per channel.
Exactly. Per tensor means you calculate one single scale and 0 point for the entire tensor, whether it's weights or activations. Simpler, but...
But if different parts of the tensor have different ranges.
Right. Imagine a convolutional layer. The weights for different output filters might have totally different distributions. One scale is 0 point for all of them, it's a compromise, can hurt accuracy. So per per channel, or per axis, calculates a separate scale and 0 point for each channel, usually along the output channel axis for conlinear weights. This adapts way better to the unique stats of each filter or neuron. For weight quantization, per channel almost always gives significantly better accuracy.
Okay, putting it all together, how do we make practical choices for, say, con or linear layer weights?
Recommendation is usually per channel. Definitely. As for symmetry, symmetric if your hardware is optimized for it, otherwise asymmetric is often safer for accuracy. Rationale, weights vary per filter, per channel is key.
Makes sense. What about activations after something like ReLU or GELU? Those are always non-negative, right?
Yeah, inherently skewed. So for those per tensor, asymmetric is typical. Asymmetric uses the range efficiently for that skewed data.
But activations after 10, those are centered around 0.
Naturally symmetric, yes. So potensor, symmetric is usually a good fit, efficient.
And for just general intermediate activations where you might not know the distribution.
Default safe bet is often per tensor asymmetric. Gives you flexibility.
Okay, we've got PTQ, dynamic, static, calibration methods, symmetry, granularity. But what if you do all that, even the advanced PTQ, and your accuracy still isn't good enough? Like, you absolutely need that near original accuracy, but also the INT8 speed and size. What then?
That's when we bring out the heavy artillery. That's when you need Quantization-Aware training, or QAT. QAT flips the script. Instead of quantizing after training, it injects the effects of quantization during the training or fine-tuning process itself. The model learns to cope with the noise, the rounding errors of low-precision math while it's training. The weights adapt, find a state that's inherently robust to being quantized later.
How does that work? How do you simulate quantization during training?
Through something called fake quantization. This is key. The training itself still happens in high-precision float like FP32. The awareness comes from inserting special nodes like PyTorch's QuantStub and DeQuantStub into the model graph during training. These faked quant nodes take the FP32 input, simulate the process, scale it, round it to the target integer grid, like INT8, but then immediately convert it back to FP32 using the same scale 0 point. So the output is still FP32, but it's lost precision. It precisely mimics the rounding and clipping errors you'd get in real integer inference.
Okay, that makes sense for the forward pass. But wait, rounding, that's a step function, right? Its derivative is 0 almost everywhere or undefined. How do gradients even flow back during training? How does the model learn?
Excellent question. That's the gradient dilemma, and the solution is a clever trick called the straight-through estimator, or STE. On the forward pass, the rounding happens normally, but on the backward pass, when calculating gradients, the STE just pretends the derivative of the rounding function is 1.
It just ignores the rounding for the gradient.
Essentially, yes. It acts like an identity function for the gradient calculation. It lets the gradients flow straight through the fake quantization node, bypassing the problematic derivative. It's an approximation, but it works remarkably well in practice.
Wow. Okay, so why go through all this? Why is QAT considered superior when PTQ fails?
Well, it's not just about clawing back accuracy points. The really profound thing, I think, is how it improves the model. QAT acts like a very specific, very powerful form of regularization. Injecting that quantization noise forces the optimizer away from finding sharp, narrow valleys in the loss landscape.
Sharp valleys being bad because
Yep.
a small change pushes you way up.
Exactly. They're very sensitive to tiny perturbations like quantization errors. QAT guides the optimizer to find wide, flat basins in the loss landscape. A model sitting at a flat minimum is inherently more robust. Small quantization errors don't drastically change the loss. So a QAT model isn't just accuracy recovered, it's fundamentally more stable for low precision deployment.
That's fascinating. So it's not just a fix, it actually encourages a more robust model structure. Still, sounds like a lot more work than PTQ. Is it always worth the effort?
It's definitely more involved, requires fine-tuning, managing the QAT setup. It's an investment. But often, especially for really sensitive models or when pushing to very low bit widths, it's the only way to hit the target accuracy. That difference it makes can be the deciding factor in whether a model is deployable on your target hardware or not. So yeah, when accuracy is paramount, that investment often pays off big time.
Okay, but even with QAT, maybe accuracy still isn't perfect, or maybe you used PTQ and hit a wall. Things can still go wrong. How do you systematically figure out what went wrong? You don't just guess.
No, definitely not guess. There's a process. First, isolate the error source. Is it the weights or the activations causing the biggest problem? You run experiments. quantize-only weights, activations, FP32, then quantize-only activations, weights, FP32. Compare those to the fully quantized and the original FP32 model. That usually points you in the right direction.
Okay, find if it's weights or activations. Then what?
Per layer sensitivity analysis. Now you zoom in. You loop through the layers, maybe one by one or small groups. Quantize just that layer or group. Leave everything else FP32. See which layers cause the biggest accuracy drop when they alone are quantized. That gives you a sensitivity profile of your model. You know the trouble spots.
Find the problem layers, and then...
For those really sensitive layers, you can dig deeper with numerical analysis and visualization. Dump the actual tensor values, FP32 versus quantized output for that layer. Calculate metrics like mean squared error, MSE, signal-to-noise ratio, SNR, between them. Visualize the distributions, see where things are diverging numerically.
And all this diagnosis leads to a solution, right? You mentioned a rescue mission. Mixed precision quantization. Sounds like you don't have to quantize everything.
Exactly. That's the key insight. Quantization doesn't have to be all INT8 or nothing. Mixed precision means you're strategic. You take those sensitive layers you identified, the ones causing the most trouble, you keep them at a higher precision. Maybe FP16, maybe even back to FP32. But the rest of the model, the less sensitive layers, they stay quantized at INT8. It's a crucial tool for balancing accuracy and performance. You optimize where you can, protect where you must.
Like using notice to exclude and ONNX runtime?
Precisely that kind of mechanism, yes. And the field keeps pushing, especially with these massive models. We're now seriously looking at sub-8-bit and block quantization, particularly for LLMs, large language models. LLMs have this unique challenge. They're huge, obviously, but they also have these systematic activation outliers. A few specific activation channels just have enormous values compared to others.
And those outliers are important.
Apparently crucial for performance. But they wreck standard per-tensor quantization. That one outlier blows up the range for the whole tensor, kills precision for everything else. INT8 PTQ often fails catastrophically on them. So that led to techniques like block quantization. Instead of one scale 0 point for the whole tensor, you divide the tensor into small blocks, maybe 64 or 128 values each, and you calculate a unique scale and 0 point for each block.
So the outlier only affects its own little block?
Exactly. It isolates the impact, preserves precision in the other blocks. This is what enables accurate quantization down to really low bit widths, like INT4, which is critical for fitting LLMs on smaller devices. You hear about things like QLoRa, double quantization. They often build on this blockwise idea. It really shows how model architectures and these optimization techniques have to evolve together. Understanding why a technique was developed helps you tackle the next new architecture.
Okay, to really tie this all together, let's walk through a hypothetical capstone project. Say, rescuing a vision transformer, a VAET. Why VIT?
VITs are known to be tricky for quantization. The self-attention mechanism, layer normalization, GELU activations, they can be quite sensitive. So the workflow would mirror everything we've discussed. Step 1, baseline. Load your pre-trained FP32 VIT, check its top 1 accuracy on your validation set. Export it to FT32 ONNX, benchmark its latency. That's your gold standard. Step 2, the naive attempt and diagnosis. Apply basic PTQSs, maybe per tensor, min-max calibration. Watch the accuracy plummet.
Okay, it breaks.
Right. Then you run that per layer sensitivity analysis. You'd probably find, say, linear layers near layer norm or softmax pop up as highly sensitive. Step 3, advanced PTQ rescue. Now you requantize. Use a better calibration method, entropy, percentile. Enable per-channel quantization for the weights. And crucially, use mixed precision. Exclude those top 3 or 5 sensitive layers you found from INT8 quantization. Evaluate again. Your goal. Recover most of that accuracy loss, still get a good speed up over FP32. Step 4, QAT for peak accuracy. If PTQ still isn't quite good enough, you go full QAT. Set up the QAT fine-tuning process in PyTorch on the FP32 model. Define your QConfig, how you want to quantize each layer type. Fine-tune for a few epochs, low learning rate. Convert the QAT model, export to ONNX QDQ format, benchmark final accuracy and latency.
And the results might look something like this, right? Let's put some illustrative numbers on it. FP32 baseline, maybe 75.8% accuracy, 330 millibit size, 25 meters latency, 1.0x speed. Naive PTQ, accuracy crashes to, say, 45.2%. Size drops to 83 MB, latency improves to 12 meters, 2.1x speed up, but that accuracy is useless.
Totally unusable.
Advanced PTQ with mixed precision, etc. Maybe you get back to 72.5% accuracy. Size is around 95 millibit, a bit bigger due to excluded layers. Latency 15 meters, 1.7x speedup.
Yeah.
Decent trade-off. QAT, you push accuracy almost all the way back, maybe 75.1%. Size is efficient, 84 in beat. Latency is good, 13.5 meters, 1.9x speedup.
Exactly. And those kinds of results let you make informed choices. Limited time, need good enough accuracy, advanced PTQ is great, accuracy absolutely cannot drop. QAT justifies the extra engineering effort.
Wow, what a journey. We've really gone from the basics, what quantization even is,
Yeah.
those core trade-offs through mastering PTQ, dynamic versus static, the whole art of calibration, granularity, all the way to the power of QAT, and even these frontier techniques like block quantization for LLMs, and that systematic debugging with mixed precision.
Yeah, and the key thing for you listening, the so what, is that you now have, hopefully, a really practical framework for thinking about how to make AI models efficient, how to deploy them effectively. Balancing that accuracy and performance puzzle is just crucial as these models get bigger and bigger and appear in more places.
Absolutely. Yeah, and maybe a final thought to leave you with. As AI continues to grow, these huge LLMs, real-time vision, think about how this subtle art of quantization isn't just an optional optimization anymore. It's becoming a fundamental enabler. And so it makes powerful AI accessible, sustainable, deployable everywhere. So the question is, what new things become possible? What apps get transformed if we can squeeze even more performance out of every single bit?